Welcome to this explainer. Today, we're diving into something absolutely wild, the foundations of mathematics. When we learn math in school, we're taught to view it as the ultimate realm of absolute truth. We believe that if a mathematical statement is true, there has to be a step-by-step way to logically prove it, right? That's literally what our computers and calculators rely on every single second to function. But, as we're going to see, the deeper you dig into the actual bedrock of numbers, the more that absolute certainty just completely shatters.
So we've got to start with a massive question. It kind of upends everything we think we know about numbers and logic. Can mathematics actually prove everything? Decades ago, Kurt Gödel blew everyone's minds with his incompleteness theorems. He basically proved that in any logical system, you are going to have true statements that simply cannot be proven. Now, for a long time, mathematicians kind of brushed this off. They figured, hey, these unprovable statements are just weird, self-referential paradoxes, basically mathematical parlor tricks that won't mess with real, everyday, practical math.
Well, reality hit hard. In 1977, mathematicians Jeff Paris and Leo Harrington stumbled onto a perfectly natural, everyday arithmetic problem that standard math simply could not solve. It was a real game changer. It instantly shattered this illusion of a perfect, bulletproof mathematical system, and it revealed that our basic logic actually has massive, undeniable blind spots.
Let's get right into Section 1, when mathematics breaks down. For decades, everyone leaned on this system called piano arithmetic to prove basic truths. It's a standard foundational system of axioms used to define the properties of natural numbers. 1, 2, 3, the whole shebang. It's the core logic underpinning basic addition and multiplication. People thought it was the absolute, unshakable bedrock of arithmetic. Until Paris and Harrington found that one natural statement that broke it entirely.
They triggered what's known as the strengthened finite Ramsey theorem. Now, this sounds like a harmless puzzle about coloring subsets of integers, the kind of game mathematicians use to break their own brains, but it actually triggers a catastrophic mathematical breakdown. The setup is, you take a set of numbers, group them into subsets, color those subsets, and then find a specific subset that's monochromatic, meaning everything in it shares the exact same color. But here is the kicker. The size of this subset has to be at least as large as the smallest number inside it.
So why is this such a big deal? Because this seemingly simple counting problem grows so monstrously fast that piano arithmetic just blue screens. It cannot process it. The smallest number needed doesn't just get big, it completely outpaces the Ackermann function, which is our most extreme tool for calculating massive numbers. It's not primitive recursive. To even prove this theorem is true, you literally have to abandon standard arithmetic altogether and use second-order arithmetic or Zermelo-Fraenkel set theory. We are forced to grab infinitely larger tools just to solve finite problems.
Which brings us to Section 2, the large cardinal hierarchy.
Since standard set theory couldn't handle these impossible problems, mathematicians had to invent, or depending on how you look at it, discover these staggeringly infinite entities known as large cardinals. We're talking about transfinite numbers so massive, so incomprehensibly huge, that their very existence cannot be proven within standard Zermelo-Fraenkel set theory. And keep in mind, that is the baseline foundation of modern math. If our standard set theory is consistent, it simply cannot prove that a large cardinal even exists.
This perfectly captures the new rule of modern math. Mathematician Dana Scott put it brilliantly, that if you want more, you have to assume more. It's basically a mathematical cheat code. You literally have to just assume the existence of these massive infinities just to prove basic truths. You have to actively bolt on new axioms to your foundational system, stepping way outside the boundaries of everything previously known.
Think of this as a massive ladder of infinity. What's absolutely wild is that these large cardinal axioms seem to line up in a strict linear order based on their consistency strength. As you move up the theory, each axiom steps higher. Some are echo-consistent, meaning if one is consistent, the other is too. Some are strictly stronger, actually letting you prove the consistency of the weaker ones beneath them. So mathematicians are just endlessly climbing this ladder, constantly reaching for higher, unprovable truths to serve as the ultimate foundation.
But this naturally pivots us away from hard logic and straight into a deep philosophical mystery. Think about it. If you have to invent an infinitely large cardinal completely outside of your system just to prove a theorem within it, did you discover that cardinal or did you invent it? What exactly is a number, really?
Let's explore that in Section 3, the philosophy of structuralism.
Back in the 1960s, philosopher Paul Benacerraf made this famous argument that numbers aren't actually objects at all. Instead, numbers are simply positions in a structure.
Think of it like a theatrical play or a blank check. The number 2 is just a role being played on stage. It's not the physical actor. All that really matters are the relationships between the positions, not the intrinsic makeup of the thing playing the part.
This brings us to a super important concept in structuralism, isomorphism. An isomorphism is basically a structure-preserving mapping between two systems. It means they are perfectly structurally identical. Because numbers are just roles, any system that is isomorphic can flawlessly play the part of the natural numbers. So whether you use one flavor of set theory or another to define the number 2, as long as the structural relationships hold up, the math works perfectly.
And right here we get a massive clash of ideas within the philosophy of math. On one side, we've got eliminative structuralism, pushed by thinkers like Geoffrey Hellman and Hilary Putnam. They want to eliminate abstract objects entirely. They rely purely on modal logic, if-then statements. They're basically saying, necessarily, if a system exists that follows the rules of arithmetic, then 2 plus 3 equals 5. But on the flip side, we have non-eliminative structuralism. This camp argues that abstract structures absolutely exist independently, as real entities, completely separate from any physical instantiation. To them, the structure itself is the mathematical object.
This debate naturally evolves into Section 4, Sets versus Categories.
This introduces category theory, which is an incredibly abstract theory of mathematical structures. It's focused entirely on objects and the morphisms, which are essentially the connecting arrows or relationships between them. Instead of obsessing over what a mathematical object is literally made of on the inside, category theory only cares about how that object interacts with everything else around it. It's basically structuralism brought to life as a rigorous mathematical tool. When you put these dueling paradigms side by side, you see a fundamental shift in how we view reality. Set theoretic foundations build the universe from the bottom up. A set is defined by its internal members, creating an assertic universe, meaning it asserts that specific hard and fast items actually exist. But category theoretic foundations, they offer a top-down characterization. Objects are defined entirely by their mapping properties. It's syntax invariant and purely structural. It doesn't ask, what is this made of? It asks, what does this do? It's a massive shift from seeing math as just static, contained sets to viewing it as this dynamic web of purely structural relationships.
So where is all of this heading? Section 5, the future of truth. Mathematician Hugh Wooden has proposed an absolute master framework, an expansion on Gödel's work called Ultimate L. This is a proposed axiomatic foundation for set theory that tries to finally unify this chaotic web of unprovable truths and endless infinite ladders. Wooden is essentially hunting for the ultimate mathematical universe that can safely house all those large cardinals, serving as a grand finale to this entire foundational mystery.
The consequences here are staggering if Ultimate L becomes the new foundation. First off, it implies the continuum hypothesis, which would finally solve a century-old riddle about the different sizes of infinity. Second, it neatens everything up by reducing all questions of set theory strictly to axioms of strong infinity, organizing everything according to the power of large cardinals. And third, it provides a foundation completely immune to mathematical independence by Cohen's method, meaning we wouldn't be plagued by true statements that are provably unprovable anymore. If it holds up, this mind-blowing proposal gives us a complete, unified picture of mathematical infinity.
We've journeyed all the way from basic arithmetic breaking down to the invention of massive infinite cardinals, straight through the philosophy of structuralism, and right into today's ultimate unified theories. So I want to leave you with this final provocative thought. If mathematical truths actually require unprovable infinities to function, and if numbers are merely structural roles rather than real objects, is mathematics a fundamental discovery of the universe, or is it simply a masterful invention of the human mind? The deeper we zoom out into the foundations, the more mysterious reality becomes. Thanks for exploring this explainer with me. Keep wondering and keep learning.